Okay, let's pray. Father God, we thank you, Lord, for this day. We praise you, Father God, for your goodness, Lord God. We thank you, Father God, that you are Lord over all, Lord God. And we just praise you, Father God, for this day, for this week, for this time, Father God. We are made for such a time as this, Lord God. And so we thank you, Father God, that we are equipped, we are well equipped to do what you have us to do, Lord God. Keep our eyes focused on you, Father God. Keep our thoughts in line with you, Lord God. Give me the words you have me to speak, Lord God. Give us all listening ears, Lord God. We praise you in Jesus' name. Amen. Amen. Well, welcome, guys. Welcome again. We are in a new section, section 5.2. It seems like we're going backwards. We were just in section 5.3. And in some ways we are. I'm jumping around a little bit. I'm skipping around vector spaces. I'm going to hit vector spaces at the end of the semester if I have time to do that. But I wanted to make sure I get some of the core things done and talked about so that you've seen it before. Vector spaces are important. Vector spaces are super important. I know that. And I'm going to talk about that, but I want to make sure that some of these ideas and concepts that you see in linear algebra, you see in this class before the semester is over. So we're going to move around vector spaces for right now, and we're going to go to section 5.2. So I'm going back one section. The inner product spaces. Inner products, actually. And what we want to say here is that inner products, so actually, topics for the day. Topics for the day. Let me not get ahead of myself. I'm going to look at the definition of the inner product. We're going to talk about distance, angle, and projection. Okay. And then we might do a little bit of Gram-Schmidt using this idea. Okay. So definition of inner product, distance, angle, and projection. And then we might do a little bit, just a teensy bit. Actually, no, we won't. We won't do any Gram-Schmidt. I'm going to take that off. Nobody wants to see anyone Gram-Schmidt. Let's keep it simple. This is enough to tide us over this semester, I think. Definition of inner product, distance, angle, and projection. But you can extend this idea to Gram-Schmidt, but we're not going to do that here. Okay. All right. So let's get started. And we can say that inner products are generalizations of the dot product in Rn. Now remember what the dot product did, right? Remember what it did. The dot product was used to allow us to talk about the distance between two vectors. It allowed us to talk about the length between two vectors. It allowed us to find the angle between vectors, right? It allowed us to do projections of one vector onto another vector, right? Because of the dot product, we're able to do all of these things. And what we want to do is I say, okay, we have this dot product, but can we create a new dot product? Can we create a new way of measuring distance between things? Do we only have to measure distance between vectors? Is vectors the only thing that we can measure distance between? Or can we measure the distance between functions, right? And so this is the idea of the inner product. Inner product says, okay, as long as I have two mathematical objects, I want to be able to figure out how I can relate them in terms of distance or angle between those objects. So inner products. Okay. Inner products have to follow certain rules. So that's what we want to write down now. Here's our definition. an inner product on a space V, okay? On a space V, so this could be a, like Euclidean space like R2, R3, R4. It could be like what we had before, where we had matrices of size 2 by 2, you guys remember that? Or polynomials, or complex numbers. So it could be any type of space we're talking about here, because I want to be able to talk about the distance between complex numbers too, right? Those types of things. And we call this, and the notation for the inner product is going to be a angle bracket, U with V. U and V are going to be my two vectors, or my two mathematical objects, is a function that associates a real number to a pair of vectors, or whatever my mathematical objects are, U and V. So whenever you take an inner product, it gives you a number back. So it's you give it two vectors or two mathematical objects, and it spits a number back at you. Now there are some rules that it has to follow, and these are called axioms, rules that it has to follow. The first rule that it has to follow is that it doesn't matter the order in which you put the two vectors in. The inner product of U and V is the same as the inner product of V and U. Two, the inner product of U with V plus W, where W is another vector. This is the same as the inner product of U and V plus the inner product of U and W. So kind of like a distributive property. Three, if I multiply the inner product of U and V by a scalar, let's call it C, this is the same thing as saying the inner product of CU with V, or U, the inner product of U with the vector CB. Right? So that C can go either on the U or on the V. Okay? The C does not go to both U and V, it just goes to one or the other. Four, the inner product of a vector with itself, or a mathematical object with itself, has to be greater than or equal to 0. Because this is how we're going to define our distance. We're going to define our distance using this particular property. And finally, number 5, I'm going to squeeze it down here. You have it in PowerPoints as well, 5. The inner product of V with itself is equal to 0 if and only if V equals 0. So what does this mean? The 0 vector. What does this mean? If my inner product is equal, when I take V with itself is equal to 0, then that means V has to be equal to 0. If V is equal to 0, then the inner product of V with itself has to be equal to 0. That's what the if and only if statement says. That's what it's talking about. Okay, so we have that. And these are properties that all inner products have to have, right? These are properties that if you have an inner product, it has to satisfy all of these properties. So you can, if you have something where you have 3 vectors and you look at the inner product of U and V plus W, right? You can break it up that way. Okay? We're not going to go into a lot of detail about it. I mean, you can play around with it for yourself. But what we want to do is we want to keep it relatively simple. Relatively simple. I'm going to introduce 2 more things. The norm of U given by the norm of u is equal to the square roots of the inner product of u with itself. If you guys remember before, when we wanted to find the norm of a vector, right, it was the square root of the dot product of u with itself. You guys remember that? It was a long time ago. Look back in your notes, you'll see that. Only thing we're doing is replacing the dot product with this inner product symbol. You're like, Dr. Wesley, you have told us what the inner product looks like. And the thing is, I can make my inner product whatever I want as long as it satisfies these conditions. And we're going to look at some examples of that. And another thing to say is the distance. Between two vectors. U and V is given by, you've seen this notation before, D of U and V, which is equal to, if you guys remember, the norm of U minus V. That's how we define our distance. And it's the same, this is the way we defined our distance a long time ago, it's the same way we define it now. Let's look at some examples of inner products that we can use. We'll start off with ones that are easier, right? Staying in Euclidean space, and then we'll look at some inner products in different spaces that are not Euclidean space. Here's an example. I'm going to be looking at a weighted Euclidean inner product. We can think of this as a weighted dot product. And here is just one example of many weighted Euclidean inner products. I could have made a different weighted Euclidean inner product. But here, let's say let U be a vector U1, U2, okay, and V be a vector with components V1, V2, in R2. Okay. So we're in R2. Then I can create a weighted Euclidean inner product. I'm going to call it U, V. And the form of this guy is that I'm going to have, what do I have here? 3 times the first components plus, here I have 2 times the second components. And what this says is that I give more weight, I give more value to the first components than I do to the second components, right? Because if whatever the first components are, right, I'm going to do 3 times that, so it's going to have triple the weight. Well, we have this relationship that this is going to be 3 versus 2, right? If they were equal weight, right, this is very similar to what we already have, where for our dot product, where our weights are just 1 and 1, right? I have 1 times U1 V1 plus 1 times U2 V2 for a regular dot product. But here I have 3, so this one's going to have more weight put on it. The first component is going to have more weight put on it than the second components. Okay. What am I going to do with this? I want to, let's just use some numbers here and do an example. I want to do an example. If U is equal to 5, 2, and V is equal to 1, 1, find A, the inner product of U and V, B, the inner product of U and 3V, C, the norm of U, and D, the distance between U and B. Okay. I want to find the inner product of U and B, the inner product of U and 3B, the inner product, the norm of U. And the last one is the distance between U and B. Well, let's look at the first one, right? The inner product of U and B. It says, this inner product says I'm going to do 3 times the first components, which are 5 and 1, plus 2 times the second components, U2 and B2, 2 and 1. When I multiply that, I get, what is that, 19? Let's go ahead and look there. What about the next one? What about the next one? Well, I need to know what is 3 times B. What is 3 times B? 3 times B is equal to 3, 3. Okay. Have that right there. Put that in the cloud. Now let's do this. U, 3B, so I have 3 times the first components. So the first component of U is 5, the first component of 3B is 3, so it'll be 5 times 3. Plus 2 times second components, 2 and 3 there, 2 times 3. And that is equal to, what is that equal to? Let's see, 15 times 3, it's 45. 45 plus 12, is that 12? Yeah, 45 plus 12 is, what's that, 57? 57. And notice that 57 is 3 times 19. 57 is 3 times 19. Now, why is that important? Because remember, I have rule number 3 here, right? And rule number 3 says that if I have U, the inner product of U times C times B, right? I can essentially pull that C out and put it to the front. So I could have really thought of this as the inner product of U and V times 3. And that's the same thing, so that'd be 19 times 3, which is 57. If you didn't get that, that's okay. But if you did, that's kind of neat, right? That's pretty neat. And I really want to talk about it more, but let's keep going. What's the norm of U going to be equal to? The norm of U, when we look at this, it's going to be equal to what? Well, the square root. Square root of what? U with itself. So I take U with itself. So I do 3 times the first component of U, which is 5, with itself, which is, again is 5, plus 2 times the second components, right? But it's going to be U with itself, so it's going to be 2 times 2. Goodness, what's that? 25 times 3, 75, right? 75 plus 8 is 83, so I get square root of 83. And that is going to be my distance using this weighted Euclidean inner product, which puts more weight on the first component than it does on the second. And what about the distance between U and B? Distance between U and B. Okay, and first thing I need to know, what is U minus B anyway? I know that this is equal to the norm of U minus B. What in the world is U minus B? Let's find out what that is. U minus B, so I do 5 minus 1, that's 4. 2 minus 1 is 1. Okay? So essentially I do the same thing I did over here, right? Where I say, okay, now I'm using u minus b, so I have square root of 3 times 4 times 4, which is going to be 4 squared. Can I write that 4 squared? Because it would be 4 times 4, just like over there, it's 5 squared. Plus 2 times 1 times 1, which is 1 squared. Oh goodness, 16 times 3 is 48. 48 plus 2, that's 50, if I did that right. So I get square root of 50. That is a distance between u and b. And you can think of this as almost like a cost function. Maybe it costs more to go in the x direction than it does in the y direction, right? So think of this maybe as fuel price, maybe, or something like that, or maybe there's issues, there's a cost or tax going in the x direction that's higher than a tax going in the y direction, right? So you can think of this as almost like a cost function, right? It kind of tells you what would be the cost of going a certain distance. Okay. So this is my weighted Euclidean inner product. And that one's pretty neat, but let's do another one that is a little bit different, right? We're used to r squared, but let's pick a different space. I'm gonna erase this. And we have an inner product on functions. A function is a mathematical object. So I want to be able to talk about distance with this mathematical object like I was talking about distance between vectors. Why not? So here I have my setup. Let u equal f of x. Okay, I'm going to act like it's a vector, u equal f of x, and v equal g of x, be two continuous functions on c negative pi to pi. Now what this means, this is a little bit of an interesting notation. This means continuous functions on interval negative pi to pi. Essentially, this is a set of all continuous functions on the interval from negative pi to pi. This is what this c negative pi to pi means. Then, an inner product for the functions are, in this case I'm going to use u and v are equal to the interval from negative pi to pi of f of x times g of x dx. Now notice that this will give me a number, a real number when I integrate this. So I get a real number. So I'm taking two functions, f and g. Now here, only thing I care about is that f and g are continuous on the interval from negative pi to pi. That's the only criteria for these functions. If I were to integrate this, I have to make sure that those two functions that I'm integrating are continuous from negative pi to pi. That's the only restriction I have to be able to use this inner product. And what I want to do is I want to find and we'll keep it relatively simple. A, the inner product between u and v. and B, the distance between you and me. The distance between you and me. I haven't told you what F and G are. I should tell you that, right? Let's see, where did I do those with those guys? So here I'm gonna say U is equal to sine of X, and B is equal to cosine of X. Those are these two functions are continuous from negative pi to pi and beyond, right? They're continuous for all real numbers. So if I take the inner product of U and B, I get negative pi to pi sine of X, which is my F, times G of X cosine of X dx. Now when you integrate this, notice what you get. You're going to end up with 0. I end up with 0, right? When I take the inner product of sine with cosine, I get 0. 0 is my answer. Now this is interesting. We're going to talk a little bit more about this, right? But remember what happens. What did we say when our dot product was 0? When we had two non-zero vectors, right? And we take the dot product and we got 0. What did we say those two vectors were? We said that they were orthogonal, right? Here I have an inner product, and these two vectors, when I take the inner product, I get 0. I could say the same thing. Sine of X and cosine of X are orthogonal relative to the inner product that I've used here, this inner product that I created. So relative to this inner product, sine and cosine are orthogonal to each other. These guys are orthogonal functions. Okay? That's pretty neat. And what about the distance between U and B? Well, what is U minus B? U minus B is sine of X minus cosine of X. That's as far as I can go. So when I find the distance between these guys, that's going to be equal to the square root, right, of my inner product of U minus B with itself. So it's going to be negative pi to pi. Essentially, sine minus cosine of X will be both F and G. So I get sine of X minus cosine of X squared, because I have, this is essentially going to be my F and my G in my inner product, right? So sine of X times sine of X minus cosine of X times sine of X minus cosine of X dx. And what do you get when you do this? You end up with square root of 2 pi. Square root of 2 pi is what you end up with. Right? So the distance between sine of X and cosine of X is square root of 2 pi. Which seems weird, right? But what I want to do is I want to extend this idea of distance, right? Why are vectors so important that they're the only one that have distance, right? Why can't functions have distance between them? Why can't matrices have distance between them, right? Why can't complex numbers we know have distance between them, right? Why should we restrict ourselves, right? We can talk about distance between two functions. The distance between these two functions is square root 2 pi. Relative to this inner product that I made here. And remember, we just said that when we said that sine of X and cosine of X are orthogonal to each other, right? Because their inner product is equal to 0. But I want to be able to talk about the angle between two mathematical objects overall, right? And we can talk about angle between two mathematical objects. That's what we want to talk about next. angle between two non-zero vectors. Is given by theta equals arc cosine of the inner product of u with v, all that divided by the norm of u times the norm of v, where theta is between 0 and pi. And we can say that u and v are orthogonal when u dot v is equal to 0. Or I can say it the other way. This is actually if and only if statement. If u dot v is equal to 0, then they are orthogonal. If they're orthogonal, u dot v is equal to 0. Okay, so it goes both ways. So I want to extend this idea. And here I have it, notice that orthogonality depends on the inner product. So if you have a different inner product, things that were orthogonal before, if you change inner products, might not be orthogonal anymore. Okay. So we have to be careful there. But relative to the inner product that you choose, these two guys will be orthogonal if my inner product is equal to 0. And then we also have the idea of orthogonal projection. And so I can say the projection of a vector v onto u, or vice versa, right? Right, so I want to project my mathematical object onto another mathematical object. This is equal to the inner product of u and v over the norm of u squared times u. So this is essentially the same thing we've already done. My dad said same old soup, just heated over. We're replacing the dot product with this inner product statement, right? And we define what the inner product is, right? We define how we want to think about distance. Let's look at an example. Here it is. Let the inner product on P2. Now remember what P2 is. P2 is polynomials of degree 2 or less. So polynomials of degree 2 or less be given by P2. Polynomials of degree 2 or less given by this inner product. Let's suppose I have f and g, right? F and g are just my u and my v, okay? It's equal to f evaluated at a -1 times f evaluated at g. F evaluated at -1 times g evaluated at -1 plus f evaluated at 0 times g evaluated at 0 plus f evaluated at 1 times g evaluated at 1. Okay. where f and g are both polynomials of degree 2 or less. Okay. So I'm going to write over here because I ran out of space. That will happen a lot because I write a lot. Next, this. If f is equal to -2 plus 3x plus 2x squared, and g of x, g, say g, is equal to 4 minus 3x squared. Okay. Using the inner product above, find A, the angle between F and G. And let's just do these one at a time because I'm going to run out of board space. I want to be able to erase that angle formula that I have there. The angle between F and G. The angle between F and G is what I want to be able to find. So they tell me what F and G are, right? So F is -2 plus 3x squared plus 2x squared. G is equal to 4 minus 3x squared. It would be probably beneficial if I actually figure out what is the values of F and G at -1, 0, and 1 first. So let's do that first. So F at -1, G at -1. Okay. So when I plug -1 into F, see if I do this correctly, I get -2 minus 3 plus 2. So that gives me a -3, I believe. Plug -1 into G, I get 4 minus 3, I think that's 1. Let's plug 0 into F and G. 0 into F, I get -2 plus 0 plus 0, so -2. 0 into G, I get 4 minus 0, that is 4. Then finally, I want to plug 1 into F and G. Okay, so if I do 1 into F, that is -2 plus 3 plus 2, that is a +3. And when I plug 1 into G, I get 1. 1. Yep, 1. All right, so if I want to find the angle between F and G, all right, I need to find the inner product between F and G divided by the norm of F and the norm of G. That's what I need to do using this formula. So let's find the inner products and the norms. Let's find each one of these guys. What's the inner product of F and G? Well, going by the equation that we have here, right, we will multiply these together, then multiply these together, and multiply these together, then add them all, right? So let's see, that'd be -3 times 1 plus -2 times 4 plus 3 times 1. I think the 3's and the -3 are going to cancel, so I end up with -8. Okay, so that's the inner product of F and G. What is the norm of F going to be equal to? Well, I know there's going to be a square root, right? And so when I do the norm of F, right, I just use the value of F twice, right? So this becomes -3 times -3, so -3 squared, plus -2 times -2, so that's -2 squared, plus 3 times 3, that is 3 squared. Oh goodness, 9 plus 4, that's 13 plus 9, is that right? 13 plus, oh, is that 13? 13 plus 9? Is that right? Did I do that right? Yeah, I did. Square root of 22. Okay, square root of 22. And then the norm of G is going to be, we'll do this one, take the value of G twice, so it'd be 1 squared plus 4 squared plus 1 squared. And that is 16 plus 1, 17 plus square root of 18, this I think is what I get here. Okay. So theta is equal to arc cosine of negative 8 over square root of 22 times square root of 18. Let me see what that is. I think I screwed it up. I put square root of 23 last time. I get 113, essentially 113 degrees. Right, this is going to be an obtuse angle, not obese. Obtuse angle that we have here. And the next question, if you look at the PowerPoints, if you're looking at the PowerPoints, is, where do I have it? Do I have the right thing? Next question is, are F and G orthogonal? All right, there we go. Are F and G orthogonal? And I can say that they are not. No, right? If they were orthogonal, then this would be 0, right? For my angle between F and G. I mean, it won't be 0. This would be 90 degrees, 90 degrees. If F and G were orthogonal to each other. They're not orthogonal to each other at all, right? Or the inner product of F and G would be equal to 0, right? We would have been able to see that in the very beginning. So we know that F and G are not orthogonal. See? And what's the orthogonal projection of G onto F? So what is the projection of G? Do I have G onto F? The projection of G onto F. What is the projection of G onto F? Right? That's what I want to know. Here's my orthogonal projection, but it's not that bad, right? We just have to be careful. Projection of G onto F, that's going to be the inner product of F and G, which we already have, over the norm of F squared times F. What is the inner product of F and G? Well, it's negative 8. What is the norm of F squared? Well, it's going to be 22. Okay. What is F? Well, F is negative 2 plus 3x squared, plus 3x plus 2x squared. And then if I want to, I can simplify that. What is that? That's like negative 4 over 11, something like that. This is negative 4 over 11, so I think if you simplify, you get 8 over 11. Oh my goodness. Minus 12 over 11. Yeah, I think. X, and then this is going to be negative 4 over 11, so this is going to be negative 8 over 11x squared if I didn't screw up, if I know how to multiply together. And so that's the projection of G onto F. Okay, and this is what we have here. So that's pretty neat. Pretty neat stuff there. Of course, we can extend this idea of projections, right? Instead of just projecting onto one mathematical object, we can project onto a subspace, just like we did before. So I can project my mathematical object not only onto another mathematical object, but onto a subspace of mathematical objects. What I usually like to say before we get there, I want to say just a little bit about orthogonal projection. And an orthogonal projection, I like to take my time to talk about it, but you can think of an orthogonal projection as the closest approximation of the function, or whatever your vector is, the closest approximation of that particular function using another function. So what's the closest approximation of G, 4 minus 3x squared, using F, is what we're saying here. So what is the closest function to G using only the value of using F as a basis? And the closest function to G using F as a basis is this function right here. Okay. This guy right here. This is going to be the closest function to G using F. Right? So when we talk about doing an orthogonal projection onto a subspace, we're saying what is going to be the closest approximation to that particular mathematical object using the other mathematical objects of my subspace. I don't know if that made any sense, but it makes sense in my head. So we're going to have to keep going. Let me just erase this, and then we'll talk about orthogonal projection onto the subspace. All right. So here it is. Orthogonal projection onto a subspace. And it says this: if B1, B2 through BR is an orthogonal or orthonormal basis. For a subspace W. In a space V. Okay, it could be a Euclidean space, it could be a polynomial space, it could be complex space, it could be matrix space. Okay. Then the orthogonal projection. Of a vector U in V onto W is given by this projection of U onto W, and we've actually seen this before, right? It's going to be the projection of U onto V1 plus the projection of u onto V2 plus projection of u onto VR. But this is where it gets interesting, right? Because before we use the dot product, right? In section 5.3 we use the dot product, but we don't have to use the dot product. We can actually use the Euclidean inner product to replace the dot product. So we replace it like this. So we have u. The inner product of u would be what? Over the norm of V1 squared times V1 plus the inner product of u with V2 over the norm of V2 squared times V2 plus u times the inner product of u with VR over the norm of VR squared. And the projection is the closest in terms of distance approximation of u using the vectors in W. The projection is the closest approximation of u using the vectors in W, which is really neat. And it brings me to my last example, right, that I like to do, which is introduce you to the idea of Fourier series, because this is where Fourier series come in. What we're going to do is we're going to approximate a function. We're going to approximate a function using sines and cosines. We're going to approximate a function using sines and cosines. So I want to know what's the closest approximation of this particular function using sines and cosines. And this is the idea behind Fourier series. Okay. Let's look at an example. The last example for the day. I'm going to erase this. Here it is. Last one, guys. Let W equal the span of 1 cosine of x, sine of x. Be a subspace. Subspace on the vector space, on the space, I should say. It is a vector space, but let's not say that. On the space of continuous functions on the interval from negative pi to pi, with inner product given by this. Inner product of f and g is equal to interval from negative pi to pi of f times g dx. F and g are functions. I want you guys to notice, remember that when we do orthogonal projection and orthonormal projection, we have to have an orthogonal or orthonormal basis. And guess what? This set of vectors are orthogonal to each other. These set of vectors are orthogonal to each other, right? If you were to take any pair of vectors using this inner product, you end up with the value of 0, right? On the inner, when you find the inner product between any of these three vectors, okay? When you pair any of these three vectors. So this set is an orthogonal set, So we have that, so we can do a projection. So I'm gonna say find. So I need to give you a U. What's my U in this case? I'll pick a U. Here we go. Find the projection of the function x squared minus x onto W. Find the projection of x squared minus x onto W. Okay. So let's do that. I want to find the projection of x squared minus x onto W. Fair enough. No problem. We're okay. Breathe in, breathe out. I'm freaking out just a little bit, Dr. Wesley. I want to find what's the best approximation of x squared minus x using the functions in W. So I have x squared minus x in W. That's going to be equal to the projection of x squared minus x onto 1 plus the projection of x squared minus x onto cosine plus the projection of x squared minus x onto sine. Okay, so this is my last video for the day. So hopefully next time you see a video from me, if I'm able to do another video and not just do I might do a video, but you might just see my hand. If we're able to come back on campus again, then you'll be able to, I should have a different shirt on, right, for one thing, another shirt. That would be wonderful, right? Like Dr. West is just wearing the same shirt for 3 weeks in a row. Man, what's going on? All right, that's just free. All right, so what we have here? So what's going to be the projection of x squared minus x onto what? Well, it's going to be the same thing as the inner product of x squared minus x with 1 divided by the norm of 1 squared times 1 plus. We're going to look at the inner product of x squared minus x with cosine of x divided by the norm cosine of x squared times cosine x plus the inner product of x squared minus x and sine of x divided by the norm of sine of x squared times sine of x. Okay. Very, very good. Well, this is all great and all, but what in the world are these inner products, right? So we need to find those. So let's erase this stuff. So we have an idea of what we're looking for now, right? So let me find all the pieces and then I'll combine them together over here. So let me erase this part. Some of you guys are asking, what happens if you don't have an orthogonal basis, right? As long as you have a basis, then you can use Gram-Schmidt, just like you did before, to be able to come up with an orthogonal basis, right? But instead of using the dot product, you will be using the inner product or whatever space that you're in. So let's take each one of these components here. So I have x squared minus x 1, right? That's going to be the same thing as if we use this inner product, we have negative pi to pi, right? In this case, my f is x squared minus x times 1 dx. So that's what that's going to be, right? Then I need to do x squared minus x cosine of x. Let's just do that with x. It's going to be the integral from negative pi to pi, x squared minus x cosine x dx. Okay, just going to take care of that one. And then the last one here, x squared minus x sine of x, inner product of those two guys. Could be negative pi to pi, x squared minus x sine of x dx. Okay, have those. Are we done yet? No, I need to have the norm of 1. So what is the norm of 1? And then we can square it later. Norm of 1 is going to be, well, let's look at the norm of 1 squared, because the norm of 1 is going to be the square root of all this stuff. So if I put the norm of 1 squared, then I don't have to write the square root. That would be, that's beautiful. That's beautiful. All right, so that would be negative pi to pi, right? I'm going to use my f and g are exactly the same. They're going to be 1, so it'll be 1 times 1 dx. The norm of, what is the next one? Cosine of x squared is equal to negative pi to pi. Okay? It'd be cosine of x times cosine of x. I can say cosine squared of x, right? And then I have the norm of sine of x squared. That'd be negative pi to pi. Sine of x times sine of x, so I get sine of x squared dx. Now guess what? I need to find the value of all of these 6 essentially inner products. I have them on my sheet here. Let's see, what do I get for the first one? The inner product of the first one I have as 2 pi cubed over 3. 2 pi cubed over 3. The second one I get to be negative 4 pi. Okay. So the third one I get to be negative 2 pi. For the norm of 1 squared, I get that to be 2 pi. For the fifth one, I get it to be pi. And for the sixth one, I also get it to be pi. Okay. So let's form this together like Captain Planet, coming back over here, right now that we have all these values. Plug it in, so we get 2 pi cubed over 3 divided by 2 pi times 1, right? Plus, this becomes minus 4 pi. And so just make it a minus, right? So I say minus 4 pi divided by pi times cosine of x. Okay. And then I have another minus 2 pi, so I do minus 2 pi divided by pi times sine of x. And if I work this out, I think I get pi squared over 3, right? Minus 4 cosine of x minus 2 sine of x. This is what I end up with. I got pi squared over 3 minus 4 cosine of x minus 2 sine of x. Now I want you guys to notice, again, that this is going to be the closest approximation. This is the closest approximation to x squared minus x using only 1 cosine of x and sine of x as a basis. Okay? Closest approximation to x squared minus x using 1 cosine of x, sine of x, on the interval from negative pi to pi. Only interval from negative pi to pi, right? If you have an opportunity, I want you to go home and graph this and see how good it is, right? Now, the idea of Fourier series is that you can extend this idea, right? Instead of using just cosine of x and sine of x, you can say cosine of 2x and sine of 2x, cosine of 3x and sine of 3x, cosine of 4x and sine of 4x. And you just add as many of these sine and cosine functions as you want and see what would be the best approximation of your original function using essentially these sine and cosine functions, right? This is the idea of Fourier series. And so it kind of wraps it, so you can kind of see why inner products are useful in the first place. Like, why in the world do I care about inner products, right? It allows us to do stuff like this. We can do orthogonal projections, right? Stuff that we couldn't do before. All right, I think that is it. Well, I hope to be able to make more videos for you guys. Hopefully, in front of the board. I like doing videos in front of the board. But if we are on a lockdown, then I won't be able to do any more videos on the board. I'll try to get one at home if I can, a whiteboard, but I can't guarantee I will. And so I'll do whatever I can to be able to present the material to you guys. I hope this was at least a little bit understandable. We will talk about change of basis next time, and then after change of basis, we will go back to vector spaces. All right? Talk to you guys later. Bye.